Okay, today we discuss about this scaling and transistor scaling. Okay, so we'll see the what is this transistor scaling. Okay, transistor scaling is nothing but suppose this is the my MOSFET. Okay, so this is my MOSFET. So as you know that from the Moore's law, so Moore is nothing but is a one second. I'm sharing my screen. Sorry, I'm sharing my screen. Yeah, I'm sharing my screen. So here, Moore is a founder of Intel. He given a statement that transistor count doubles for every 18 to 24 months. So that means, so every time, that means you need to this is my transistor. So you need to scale down. Okay, suppose this transistor count is 1000. Okay, 1000 in this module. Okay, within 1 year, 18 months or 1 year, this becomes how many? This becomes 2000, and within next consecutive year it becomes 4000. Okay, next consecutive year it's not clear. 1 second, 1 second, please wait. Now is it clear? Use this one.
Yes, sir. Yes, yes, clear.
Okay, sure. So here, so transistor count. Suppose if you consider the transistor count, so the transistor dimensions. What are the dimensions? So that means number of transistors will be doubled for every 1 year. Okay, every consecutive year. Okay, so it becomes 1000, 2000, and 4000 and 8000 like that. Okay, so based on my requirement, you need to scale down this what we call, we already seen the MOSFET, no? So MOSFET enhancement and depletion MOSFET. Suppose this is the diagram for the MOSFET. So basically we are using CMOS technology. CMOS technology means we are using PMOS as a pull up and NMOS as pull down. So means at last we will come to the MOSFET only. So MOSFET have like P-type substrate and N plus regions, and we already seen like you have. So we are talking about technology. So technology means 100 nanometer technology. Okay, 100 micrometer technology, or now we are talking about 7 nanometer and 3 nanometer technology. Technology is nothing but this length. Okay, length of the channel is nothing but technology. Okay, so we are integrating some millions of transistors within an IC. So day by day the integration means whatever the number of transistors are there, number of transistors are miniaturizing, means number of transistors are increasing. Okay, some millions of transistors are there. Here you need to know about scaling. Okay, suppose this is width of the channel and this is length of the channel, and this is thickness of so this is thickness of the channel. Okay, and this is thickness of polysilicon. Okay, thickness of polysilicon, and these n plus regions are nothing but by diffusing these dopants. Okay, n plus regions we can dope this. So these are nothing but we see in source and drain. Okay, so that is nothing but scaling. Okay, we need to do the scaling of this transistor. Okay, so for this we need to do scaling of different regions. Okay, so uh, so scaling can be done in the two factors. What are those factors? Means scaling. Yeah, so scaling can be done in two factors. Okay, so scaling can be done in two factors. What are those factors? Means those are nothing but alpha and beta. Okay, so alpha is nothing but first we'll see the beta. So beta is nothing but scaling factor, thickness of oxide and voltages. Okay, so this is the scaling factor of thickness thickness of oxide, okay. So you have a oxide, no, that is silicon dioxide, SiO2 layer, okay. So the thickness of oxide is D, okay. And voltages means what? For the CMOS you are giving some biasing voltages, like whatever may be the voltages, like VDD or VGS and VDS. All these voltages, those are nothing but biasing voltages, okay. And alpha is a scaling factor for all other components. Alpha is the scaling factor for all other components, okay, all other components, okay. So here beta is smaller, compared to alpha, okay. So like this you have total you have 14 scaling factors that we will see, okay. Scaling factors for device parameter. What are the scaling factors for device parameters? Now you understood why we are going for scaling. That means like depending on our requirement, so as per Moore's law, the transistor counts double for every consecutive 1 year. So that means we need to integrate more and more transistors in the within an IC, okay. So that means we are, so like last 10 years back or 5 years back, we are working on a micrometer technology. Now we came into nanometer technology. That means the length between source and drain is that much, okay. That is the technology, okay, we are talking about. And scaling, okay, factor, device parameters, okay. What are the scaling factors? We'll see, okay. Scaling factors for device parameters. First we'll see the scaling factor, that is the gate area. Scaling factor for gate area, okay. What is the scaling factor for gate area? We'll see, okay. So you know that what is the area? Area is nothing but area is nothing but length into width, no. So gate area is nothing but I can call as length of the channel and width of the channel. That is nothing but gate area, okay. So here length of the channel and width of the channel, length is scaled by 1 by alpha, okay. And width is scaled by 1 by alpha, okay. From this I can say that gate area is scaled by what? So gate area is L by alpha into L by alpha, okay, W by alpha, okay. This is a dash if you take, and W by alpha. So this is L into W by alpha square, okay. So this is nothing but AG, okay, by alpha square, AG by alpha square. From this you can say that gate area. What is my gate area? So gate area AG is scaled by, gate area is AG is scaled by 1 by alpha square, 1 by alpha square, okay. So this is the gate area. So gate area will be scaled by how much time? 1 by alpha square, okay. And next, second one we'll see. Second one, that is gate capacitance per unit area, okay. Second one is gate capacitance per unit area, okay, per unit area, okay. Gate capacitance per unit area. So this is let us take C naught, okay. This is C naught, okay. So normally you know that what is capacitance? Capacitance equal to, you already studied the formula, that is epsilon A by D, okay. Now this is my capacitance, gate capacitance per unit area means that area will not include, okay. So that means gate capacitance equal to what? Epsilon oxide capacitance, that means permittivity of oxide by this distance, okay. So that is gate capacitance per unit area. So capacitance I am not considering, okay. So that means if you see oxide anyway constant, there is no scaling, okay, there is no scaling, okay. And D, okay, D is nothing but I told you there are two factors are there. One is beta and alpha. Beta is a scaling factor for what? Thickness. Okay, that is D. Okay, and voltages. Okay, alpha is the scaling factor for all other components. Okay, so here D is nothing but the thickness. So this is scaled by what? This is scaled by 1 by beta. 1 by beta. So now what is my COX? Let us take COX dash equal to what? Epsilon OX. Okay, oxide capacitance, and this distance. Okay, this is a D. D is scaled by 1 by beta. So this is beta. So this is epsilon OX by D into beta. Okay, this is COX into beta. COX into beta means what? Here, so what is the scaling factor for gate capacitance? Therefore, gate capacitance for COX, it will be scaled by beta. It will be scaled by beta. Okay, this is nothing but gate capacitance per unit area. Okay, gate capacitance per unit area. And next we'll see the gate capacitance. Gate capacitance. Okay, so gate capacitance is what? Gate capacitance is CG. Gate capacitance is what? CG. So initially you seen what? This is the gate capacitance per unit area. So area you not included. Okay, here gate capacitance is nothing but what? You need to consider the area. Okay, so that is nothing but what? So that means CG. Okay, CG by WL. Okay, CG by WL. So that means you can write C naught, no? C naught equal to what? Gate capacitance per unit area. Okay, so C naught you can write as, that means gate capacitance per, what is area? Area equal to, we already seen, area equal to what? Area equal to width into length. Width into length. Okay, so gate capacitance per unit area equal to what? You can write oxide capacitance. From here, CG equal to what you will get? C naught into WL. C naught into WL. Okay, you know that C naught is scaled by what? C naught is scaled by beta. C naught is scaled by d beta, and W is scaled by what? W is scaled by 1 by alpha, and L is scaled by 1 by alpha. Now CG is scaled by what? CG dash, if you substitute, this is C naught. Okay, so what is C naught? C naught into beta, and W by alpha, and L by alpha. So what you will get? This is equal to C naught into WL beta by alpha square. So this is equal to CG into beta by alpha square. Okay, so now CG, that is gate capacitance. Okay, so therefore gate capacitance is scaled by beta by alpha square. Okay, so that means gate capacitance per unit area is scaled by beta, and gate capacitance per gate capacitance, okay, it is scaled by beta by alpha square. Okay, so this you need to remember. Okay, and next you see, parasitic capacitance. Okay, parasitic capacitance means this is Cx. Okay, there is Cx is there. Okay, during when you go for a tool related module, there is in the VLSI ASIC or ASIC design flow also, you will get one thing, that is nothing but parasitic extraction. Okay, so parasitic extraction is nothing but what means there is a parasitic extraction. Okay, parasitic extraction. So parasitic extraction is nothing but you need to extract the resistance plus capacitance, RC. Okay, so this is nothing but extraction, parasitic extraction. Okay, so this you need to inside the chip there will be some interconnects are there, no? So that interconnects consist of what? Some resistance and capacitance. Okay, so that is nothing but you need to extract that you need to calculate the resistance and capacitance of that interconnects also. Okay, so that is nothing but parasitic extraction. So you will study in the back end. Okay, back end tool related subject you will study. Okay, so I'm trying to find out the how it is scaled parasitic extraction. So you know that so what is capacitance? Epsilon A by D. Okay, so that means capacitance is directly proportional to what? AX by D. Okay, capacitance is directly proportional to AX by D, and you know that where area equal to what? WL, no? So area is scaled by how much? Area is scaled by 1 by alpha square. Okay, you know that area equal to what? Area equal to w into L, width into length. Width is scaled by 1 by alpha, length is scaled by 1 by alpha, so both are scaled by 1 by alpha square. Okay, and D if you consider, this is scaled by distance. Okay, that is distance. Okay, suppose two oxide two different wires are there. What is the distance between two wires? Okay, so this distance is scaled by 1 by alpha. Okay, so that means you can write Cx dash equal to what? Cx dash is proportional to Ax by alpha square by D by alpha. Okay, D by alpha. So from here anyway this one alpha get cancelled, so here you are getting Ax by D into 1 by alpha. Okay, so this is Cx by alpha. Cx by alpha. So therefore parasitic capacitance Cx is scaled by 1 by alpha. Cx is scaled by 1 by alpha. Okay, so this is nothing but parasitic capacitance. Okay, and next fifth one we'll see carrier density in channel. Carrier density in channel. Okay, carrier density in channel means let us take Q1. Q1 is nothing but the carrier density in the channel. Okay, so carrier density in the channel is given by Q1 equal to C0 into VGS. C0 into VGS. Okay, so we know that what is C0? We already seen. Okay, what is C0? Here is in C0 is nothing but gate capacitance. Okay, so gate capacitance per unit area. So gate capacitance per unit area is scaled by what? Beta. Okay, gate capacitance per unit area is scaled by beta, and VGS is nothing but we already seen beta is the scaling factor for thickness of the oxide D and other voltages. So that means this is scaled by 1 by beta. Okay, and alpha is scaling factor for other components. Okay, so from here I can write so we know that so what is this C0? Okay, C0 is scaled by what? C0 is scaled by beta. We already seen. Okay, C0 is scaled by beta, and other voltages, that is VGS is scaled by 1 by beta. 1 by beta. Just you substitute. So that is Q1 equal to, let us take Q1 dash equal to C0 into beta into VGS by beta. Okay, anyway beta get cancelled, so you are getting what? C0 into VGS into unity, you are getting 1. Okay, so from this I can say that therefore Q1, what is Q1? Carrier density in channel. Okay, is scaled by 1. Okay, carrier density is scaled by what? 1, unity. Okay, so there is no scaling in the carrier density. Okay, that is scaled by 1. Okay, and next channel resistance. Okay, so channel resistance is nothing but what? That is nothing but we can call as Ron. We can call as what? Ron. Okay, so that means channel resistance means we already seen like in enhancement MOSFET, when VGS, that means when VGS is less than VT. Okay, when VGS is less than VT, there is no channel formation. When the channel is forming, that when VGS is greater than VT, then channel is forming. That is nothing but strong inversion layer. And when you are applying small value of VDS, then there is a movement of charge carriers, and the electrons will flow from where to where. Source to drain, and current will flow from drain to source. Okay, as there is a channel, so there will be a channel resistance, no? So there will be a channel. So channel is nothing but it's a conducting layer, in that charge carriers will move. Okay, so that means when the channel is there, so electrons are charge carriers, electrons or holes are moving in this, there will be some resistance will be there. So that we call as on resistance or channel resistance. Okay, so what is this on resistance? On resistance is given by L by W 1 by Q on mu. Okay, we know that. So that means I can write how it is scaling means L is scaled by alpha and W is scaled by alpha, and again 1 by mm, 1 by so anyway this mu is constant only. Okay, mu is constant only, there is no scaling. Mu is nothing but mobility. Mu is nothing but what? Mobility. Okay, it is constant only. Okay, and q1. Okay, q1 if you see so q1 we already see now. q1 is unity only, no? So q1 is unity only, and this is not scaling. Okay, so q1 and 1. Okay, anyway alpha get cancelled, so that means here you are getting same value, that is L by W 1 by q1 into mu. Okay, so this is equal to what? R on only. Okay, R on and 1. Okay, so R on and 1. So R on is scaled by what? R on is scaled by 1. R on is scaled by unity. Okay, R on is scaled by unity. Okay, so this is channel resistance. Hope you understood. Next, gate delay. This is 7th one, gate delay. Okay, so gate delay is nothing but it can be tau d or td. We can consider as tau d or td. Okay, so what is this gate delay? td equal to R on into CG. Okay, tau equal to what? Time constant. You already studied. Tau equal to what? RC, no? Tau equal to time constant. That is nothing but RC. You'll get the formula. You already studied in the in your analog electronics or pulse and pulse and digital circuits. Okay, so R on into CG. So you know that R on. Okay, R on is scaled by what? 1. R on is scaled by 1, and CG. Okay, what is CG? Previously we already see. CG is nothing but gate capacitance. This is nothing but gate capacitance. Okay, so CG is scaled by what? Beta by alpha square, no? CG is scaled by beta by alpha square. That I am writing. Okay, CG is scaled by, so CG is scaled by beta by alpha square. Okay, beta by alpha square. Okay, so that means this is now therefore gate delay. TD is scaled by what? TD is scaled by beta by alpha square. Beta by alpha square. Okay, so gate delay is scaled by beta by alpha square. Okay, and next you see maximum operating frequency. Maximum operating frequency. Okay, so maximum operating frequency is F0. Okay, so F0 is you know that frequency and time both are reciprocal, no? So here also F0 you can write as what? Reciprocal of this gate delay, 1 by TD. Okay, so as TD is scaled by beta by alpha square, F0 is scaled by what? Reciprocal, alpha square by beta. Okay, so therefore you can say that F0 is scaled by alpha square by beta. alpha square by beta. Okay, and next you have saturation current. Okay, saturation current. What is this? Saturation current. Okay, so saturation current that is nothing but IDSS. Okay, saturation current IDSS. Okay, so we already seen in the MOSFET, no, what is the saturation current? So that is IDSS equal to 1 by 2. Okay, 1 by 2 mu C naught W by L. Okay, W by L VGS minus Vt whole square. This is my drain current equation during the saturation. Okay, so that means here VGS equal to what? VGS means previously we already seen beta is scaled by what values? Scaled by thickness of the oxide and other voltages. So VGS is the other voltage, no? So VGS is scaled by what value? VGS is scaled by beta, 1 by beta, and Vt also threshold voltage is also another voltage that is scaled by what? That is scaled by 1 by beta. Okay, 1 by beta, and C naught. C naught. Okay, oxide capacitance. Okay, oxide capacitance is scaled by what? Scaled by beta. Okay, we already seen the starting. That is oxide beta is scaled by thickness oxide. Okay, so C naught is scaled by beta, and L. Okay, so L is scaled by what? 1 by alpha, and W is scaled by how much? 1 by alpha. Okay, just you substitute and try to get the current equation. Okay, so IDSS dash equal to here 1 by 2 constant. Okay, and so so mu is also constant. Okay, that is mobility is also constant. W by alpha by L by alpha. Okay, and VGS minus Vt whole square 1 by beta square. Okay, anyway alpha get cancelled. Okay, alpha get cancelled, and beta
Sir, see you.
1 second, C naught, no, C naught is
Yes, sir.
scaled by beta, no? Yeah,
Beta.
C naught is called by beta. So that is beta, 1 beta get cancelled. So this is scaled by what? 1 by beta, 1 by beta into IDSS. IDSS. So that means IDSS is scaled by what? 1 by beta. 1 by beta. IDSS is scaled by 1 by beta. Okay. So this is about the saturation current, that is IDSS. Okay, and next one we'll see, 10th one, current density.
Sir, IDSS is scaled by
IDSS is scaled by 1 by beta.
1.
Here beta get cancelled, no? 1 beta
Yes.
get cancelled, 1 by beta you'll get. COX is C naught is scaled by beta, no?
Yes, sir.
Okay, C naught is scaled by what? C naught is scaled by previously we see in gate capacitance. That is where is that C naught Cx, and where we are seeing this is gate capacitance per unit area. That is nothing but C naught. C naught is the gate capacitance per unit area is scaled by what? Beta, no? That beta I substituted here. Understood?
Yes, sir.
Okay. Next you see. Next current density. Current density, that is J. Current per unit area is nothing but current density. Okay, what is current density? In semiconductor physics also we already discussed about two current densities. Those are nothing but diffusion current density and drift current density. Okay, so their drift current density is due to electric field, and diffusion current density is due to concentration gradient. Okay, so we are interested only in the current density. Okay, that what is this current density? Current per unit area. Unit area is nothing but current density. So that means J equal to what? J equal to, that is saturation current by A. Saturation current by A. So we already know that what is saturation current? Saturation current will be scaled by how much? IDSS is scaled by 1 by beta. 1 by beta. Okay. and area is nothing but what? W into L, no, width into length. Okay, this is scaled by how much? 1 by alpha
One
square.
by.
Okay, 1 by alpha square.
Yeah.
Now you substitute, that is J dash equal to 1 by beta into IDSS divided by 1 by alpha square into A. Okay, so this is alpha square by beta into IDSS divided by A. Okay, so this is my J dash. Okay, this is my J. Okay, this is equal to alpha square by beta into J. Okay, so that means what is the scaling factor for current density? So J is scaled by alpha square by beta. Alpha square by beta. Okay, so this is current density. Okay, next, switching energy per gate. Switching energy per gate. This is nothing but Eg. Switching energy per gate. This is nothing but Eg. Okay, so Eg is given by formula Eg equal to Cg into VDD square by 2. Okay, we already seen what is Cg. Cg is scaled by what? Gate capacitance. Previously we already seen Cg. Cg is scaled by what? Tell me. Cg is scaled by beta by alpha square.
Beta.
See here, gate capacitance. Gate capacitance. Cg is scaled by beta by alpha square. Okay. So here you see. So that means Cg is scaled by beta by alpha square. Beta by alpha square. And VDD. VDD is scaled by what? Other voltages. VDD is scaled by 1 by beta. VDD is scaled by 1 by beta. Just you substitute. Okay. So that means Eg dash equal to Cg beta by alpha square, and VDD square is there. No, VDD square means this is 1 by beta square. 1 by beta square divided by 2. Okay. So here 1 beta. Okay, 1 beta will get cancelled. Okay, so what is remaining? This is equal to 1 by alpha square beta Cg into VDD square divided by 2. Okay, so Eg is scaled by 1 by alpha square beta. 1 by alpha square beta. Okay, that is nothing but switching energy. This is nothing but what? Switching energy. Okay, switching energy. Okay, and next we'll see power dissipation. Power dissipation.
A light one is
Power dissipation. Okay, per gate. Power dissipation per gate is what? Pg. Okay, Pg. Okay, so Pg you can write as power dissipation per gate. Pg you can write as power with respect to gate to source, power plus power with respect to gate to drain. Okay, gate to drain. PGS you can write as VDD square by on or on. Okay, you know that power formula, no? What is the power formula? V square by R, that is equal to I square R, that is equal to V into I. Okay, these are the formulas for the power, no? So that is supply voltage VDD square by on resistance R on. Okay, so from here I can say that resistance is anyway constant only. Okay, therefore PGS is scaled by 1 by beta square. Okay, why? Because Rn is constant only. There is no scaling on the resistance. Okay, Rn is constant only. Yeah. Okay. So PGD. So PGD if you take, so that means PGD. If you take the PGD, so PGD you can write as PGD equal to Eg into F naught. Eg into F naught. Okay, so Eg is scaled by what? We already seen, no? Eg, where we have seen Eg. Okay, switching energy per gate 1 by alpha square. Okay, so this is scaled by 1 by alpha square beta into Eg, and this is F naught. F naught is scaled by, tell me, where is F naught? F naught is scaled by 1 by alpha square by beta. Okay, F naught is scaled by alpha square by beta. Okay, so here this is scaled by alpha square by beta, alpha square by beta into F naught. Okay, this you cancel. So here PGD,
ఏం కావాలా?
PGD, just mute. I think somebody is talking. Just mute. If you have any questions, you can ask me after class. Okay, so PGD is scaled by 1 by beta square. 1 by beta square. So that means here, from here, you know that PG equal to PGS plus PGD. So PG is scaled by 1 by beta square. 1 by beta square. Okay, so this is power dissipation per gate. Okay, power dissipation per unit area. Next is power dissipation per unit area. Power dissipation per unit area. Unit area. So if you see the power dissipation per unit area, so that is a formula you can give as PA equal to PG divided by AG. PG divided by AG. So PG is scaled by how much? Previously we already seen. PG is scaled by 1 by beta square. Okay, 1 by beta square. 1 by beta square. And area, you know, area equal to what? W into L. Okay, AG is scaled by 1 by alpha square. So that means PA is scaled by alpha square by beta square. No, just you substitute. Just you substitute. PA dash equal to what? 1 by beta square into PG divided by 1 by alpha square into AG. So here you will get what? Alpha square by beta square into PG by AG. Okay, so this is square. This is PA. PA is scaled by alpha square by beta square. Alpha square by beta square. Okay, so this is the power dissipation per unit area. And last one, power speed product. Power speed product. Power speed product. PT. PT. Okay, so PT equal to what? You can write PT equal to PG into TD. PG into TD. So PG is scaled by what? PG is scaled by 1 by beta square, and TD, time constant. Okay, previously we have seen, no? Beta square by alpha square. No,
beta by alpha square.
This is scaled by time constant. Okay, scaled by beta by alpha square. Okay, so just you substitute PT dash equal to what? PG into 1 by beta square and into TD into beta by alpha square. Okay, so just beta 1 beta get cancelled. So this is PG into TD 1 by alpha square beta. 1 by alpha square beta. So PT is scaled by 1 by alpha square beta. Okay, so this is about the scaling of different parameters. Okay, first we are seen like scaling of what is scaling. Okay, so we already seen the Moore's law. So Moore's law is nothing but he given a statement that till now that statement is valid. Okay, still now that statement is proving. Okay, so every 1 year what happens, my transistor count will double for every 1 year, consecutive 1 year. So that you need to scale the different parameters. That is nothing but scaling. So scalings are two types, beta and alpha, and scaling with respect to oxide and voltage is nothing but beta, and scaling with other components are nothing but alpha. Beta is smaller than the alpha. First we see in the gate area. Gate area is scaled by 1 by alpha square, and gate capacitance per unit area is scaled by beta. Gate capacitance is scaled by beta by alpha square. Parasitic capacitance is scaled by 1 by alpha. Carrier density is scaled by, there is a unit, no scaling in the carrier density in the channel, Q on, okay. And channel resistance also there is no scaling, that is also unity. And gate delay is scaled by beta by alpha square. Maximum operating frequency is scaled by alpha square by beta. And saturation current, we wrote the saturation current equation, okay. So that during the MOSFET I told you, like it is operating in different regions like linear, non-linear and saturation. Linear and non-linear is nothing but triode region. That linear current equation also I told you. This is saturation current equation, and here I am doing the scaling. This is 1 by beta. Current density is scaled by alpha square by beta. Switching energy Eg is scaled by 1 by alpha square beta. Power dissipation per gate is scaled by 1 by beta square, and power dissipation per unit area is scaled by alpha square by beta. Power speed is scaled by 1 by alpha square beta. Okay, so this is about scaling. Yeah.